In this program, we're going to learn about the principles of flight. We'll also make a foray into flight simulators and introduce you to a brand new invention, the microwave plane. When we see a bird soaring in the sky, it looks so easy. Well, man was not made to have wings, but his dream of flying is age-old. Icarus was a hero of Greek mythology. It's said that to escape from prison, he made himself wings with bird feathers and wax. And he managed to fly, but he flew too close to the sun, the wax melted, and he fell into the sea. Leonardo da Vinci approached the problem from a more scientific point of view. He studied birds' movements, their shape, air resistance. He also drew several flying machines, but none of his inventions was ever built. What finally got men into the air was the internal combustion engine. The first flight took place on the sand dunes of North Carolina. It was 1903. During that memorable day, Wilbur and Orville Wright made 4 flights. The first lasted 12 seconds. Their craft went a distance of 36 meters. Such were the beginnings of aviation. It's always awesome to see a plane taking off. Tons of metal rising into the sky. How do they do it? Modern balloons and dirigibles have at least one thing in common with the first aerostats invented 200 years ago by the Montgolfier brothers. They require no energy to rise into the air. To lift off the ground, they use hot air or gases, which are lighter than the ambient air. But airliners, fighter planes, in fact, all jets seem to defy the law of gravity. Enormous quantities of energy, often tons of fuel, are needed for these kinds of planes to take off. So much power, in fact, that for most transatlantic flights, fuel makes up half the mass of the plane, and 20% of that can be consumed on takeoff alone. Not only does the plane have to fight against air resistance, but it must reach a critical speed, which will enable it to lift off the ground. When it has reached that speed, which varies according to the mass and design of the craft, the plane takes off. The critical speed corresponds to the moment when the thrust of air under the wings is strong enough to lift the plane. The shape of a plane's wings, both for takeoff and flight, is of utmost importance. The wings of some aircraft are asymmetrical, with the upper surface slightly domed, while the underside is fairly flat. The design of such wings is based on a principle of physics discovered 250 years ago by a Swiss mathematician, Daniel Bernoulli. When the speed of a liquid or gas increases, the pressure it exerts diminishes. Since the air passing over the upper surface of the wing has farther to go than on its lower surface, it travels faster. Thus, the air pressure exerted on the top of the wing is not as strong. This difference in pressure pushes the plane upwards. The greater the speed, the greater that force will be. That's why most airplanes require long runways to attain the critical speed they need to ascend into the air. During flight, ailerons located on the wings and tail of the plane ensure the plane's maneuvers. The wing's ailerons are movable and are activated simultaneously and reversely. When one aileron is lowered, the other rises. It is due to them that a plane can tilt to the left or to the right in a turn. The rudder, in a vertical position on the craft's tail, starts the turn. But a turn requires the simultaneous movement of both the movable ailerons and the rudder. The elevator, located on the tail wings, steers the plane upwards or downwards. When raised, the air pressure on its surface weighs down the rear of the plane, which noses up and ascends. When it is lowered, the plane's tail rises and the plane goes into a nosedive. Airplanes with propellers use piston engines, similar to those used in cars, or else turbine engines. A propeller's movement resembles that of a screw penetrating a piece of wood. The propellers catch on the air molecules and spin. Jet airplanes are equipped with various types of turbine engines. For example, in a turboprop, the air enters the front of the jet, is compressed, then mixed with the fuel, which ignites in a combustion chamber. The energy of the gases emitted by the combustion is transmitted to the turbines, which provide the thrust necessary to propel the jet. This power can be increased by adding a post-combustion device. The spent gases, which still contain oxygen, are mixed with the fuel a second time, thereby augmenting the engine's thrust by 30%. However, this device is very noisy, which limits its use almost exclusively to military aircraft. In fact, the only passenger plane that is fitted with a post-combustion device is the Concorde. All these airplanes use enriched gasoline or kerosene, but in the future, a new generation of airplanes could well be propelled by liquid hydrogen. High-performing liquid hydrogen, when consumed, produces no pollutants. Its combustion only emits steam. As a matter of fact, the aeronautics industry, like a number of others, is increasingly looking toward other sources of energy to replace traditional fuels. The early engine airplanes used oil as fuel, and they were made of wood and canvas. Just imagine the risk of fire, especially in wartime. World War I had a decisive role in the development of aviation. That became obvious 20 years later. During World War II, the British Spitfires and the German Messerschmitts engaged in battles to the death. Spirited and highly maneuverable, these aircrafts could fly at speeds of 500 kilometers an hour. Civil aviation also made great headway. Bush planes were especially designed to deal with cold temperatures and fly in the far north. Being a bush pilot meant facing the unknown, but for them it was just an occupational hazard, or perhaps pleasure. Flight conditions have changed a lot. In addition to being dauntless, pilots today must be highly specialized technicians. And to train them, one of the most frequently used methods is flight simulation. We are not in an airplane. The voice we hear is not that of an air controller. The sound is not that of an engine. And that is not really an airport the pilot sees passing in front of him. We are in a flight simulator, a highly sophisticated apparatus used for training pilots and improving their skills. The environment may be entirely make-believe, but everything that happens in it is true to life. The airplane's controls are real and may even have once been used in a real plane. But unlike a real flight, the master of command here is not the pilot. Rather, it is the instructor who sits before a cathodic screen. Before takeoff, the instructor establishes the flight parameters, the weight of the craft, the amount of fuel, the airport of departure, and the destination. It is the instructor who rules the roost. He determines what kind of climatic conditions will prevail: wind, temperature, atmospheric pressure, rain or snow conditions. Further, he will play the role of air controller and give the pilot the green light. The flight simulator, installed inside a metal enclosure, rests on hydraulic legs. Upon takeoff, the box tilts backwards. Inside, the pilot feels pushed back against his seat, just as he would if he were flying a plane. And for every acceleration, deceleration, turn or false maneuver, the legs supporting the simulator retract or extend to accentuate the feeling of realism inside the flight deck. Throughout the session, the instructor tests the pilot's skills by putting him in very difficult, even life-threatening situations, if the flight were for real. The instructor can make the airplane go through heavy turbulence, or worse, he can simulate an electrical breakdown, a blowout, or even an engine fire. All conditions which would be extremely hazardous to recreate in a real training flight. In fact, flight simulators enable instructors to put pilots through more than 100 emergency situations that could not be reproduced in reality without seriously endangering their lives. All these conditions can be recreated thanks to a powerful computer. The computer, on top of managing the flight maneuvers and following the instructor's directives, produces a 3D image on the flight deck windows. This enables the pilot to spot the various important reference points, the landing strips, airport hangars, and elevated parts of a city. The image is corrected several times per second to match the airplane's course. In addition, the computer can store the visual information relating to dozens of airports located around the world. It's up to the instructor to select the departure and arrival points. Following a serious air disaster, the prevailing climatic conditions prior to the crash can be fed into the computer. This not only enables student pilots to study the causes of the accident, but also to confront the conditions themselves. During the training session, all pilot maneuvers are recorded in the computer's memory. They can later be printed out. This enables the instructor to go over the maneuvers the pilots made, identify them, and evaluate them.
Laisse tomber, il tourne pas. Laisse tomber, laisse tomber.
What was once unique only in the field of aeronautics, equally sophisticated simulators are now being used to train and improve the skills of surgeons and police officers. In the old days, a pilot had to feel his plane, the way a horseback rider feels his mount. But today that's no longer possible. Planes have become incredibly high-performing and complex. Technology has made amazing feats possible. The Concorde gets you from Paris to New York in 3.5 hours, and work is now underway on passenger planes that will travel at 4 or 5 times the speed of sound. We've come a long way since obstinate men first flapped their wings in efforts to fly. We're even developing an airplane that will operate on microwaves. A remote control airplane being developed in Canada might soon be replacing satellites for certain telecommunications and surveillance applications. Just like satellites, the plane would fly virtually indefinitely. But unlike satellites, the Sharp would not be powered by the fuel it transports. Its power would be supplied by 2 propeller engines fed by microwave beams from the ground. In the fall of 1987, a first 20-minute flight took place with a reduced-scale prototype. For the Canadian government, instigator of the project, the objective is to launch a microwave plane measuring 40 meters, which would fly in a circle at an altitude of 21 kilometers, with a telecommunications range of 1,000 kilometers in diameter. The power required to propel the plane would be provided by several dozen parabolic antennae that would follow the craft's course. These antennae would emit microwave beams to captors located on the belly of the plane. The captors have the capacity to convert the microwaves into electricity. They are made up of small antennae which themselves convert the microwave energy into a continuous electrical current. To provide the engines and telecom devices with sufficient energy, the final version of the Sharp will be equipped with 50,000 small antennae covering an area of 140 square feet. A large portion of the electricity will be directed toward the propeller engines, and the remainder will serve to power the telecommunications equipment on board the plane. The choice of an altitude of 21 kilometers is based on the fact that it is at this distance above the Canadian soil that the winds are the least violent. This means that less microwave energy would be required to maintain the plane in flight. Also, the craft's stability is extremely important to ensure constant contact with the terrestrial stations. At a different altitude, turbulence could cause poor alignment between the Sharp's antenna and those of the Earth stations, entailing frequent communications interruptions. The new plane will be used for commercial telephone, radio, television, and broadcasting communication services. But it is also expected to be helpful in measuring atmospheric conditions, such as depletion of the ozone layer and levels of carbon dioxide. Unlike telecommunications satellites, the microwave plane could easily be brought back to Earth for the maintenance of its engines and telecommunications equipment. The Sharp has the added advantage of providing telecommunications services at 5 times less cost than satellites. Several companies are currently working on a hypersonic airplane that would climb all the way to the stratosphere at an altitude of 30 kilometers and would travel at the speed of 5,000 kilometers per hour. It could make the Paris-New York connection in just over 1 hour. On the major airlines, you are greeted with magazines, candies, drinks. To help the time pass more quickly, you can watch the latest box office hit. But then, where is the pleasure of flying? You could have more fun discovering faces or figures in the clouds.